Hello, everyone. Good evening. Welcome to another Cosmic Conversations with myself, Tiffany Woolbrick, and Kurt Spivey.
Hey,
We both work at the Ward Beecher Planetarium, and we're here to chat with you guys about all things black holes. So if you have any questions about black holes or even any comments, any stories you want to share, let us know in the comments as we go. We will be checking those as we're talking, and we hope to hear from you. If you'd like to share where you're from, we'd love to hear where you're coming from as well. And I think that's all the housekeeping things. Kurt, do you want to dive in and get our conversation started?
well, just remember the gravity of a black hole pulls, science never sucks. That's important to get up front. As we're talking about black holes, you don't get sucked into a black hole because science never sucks. So, yes, this is an area that's fascinating for a lot of people. It is one of the most mysterious things in the world of astronomy today. It wasn't until just recently that we didn't even have a picture of a black hole. And even so, there's still a lot unknown about them, a lot theorized, a lot we can see indirectly, but not a lot we can directly observe with black holes. And there is a Youngstown connection to
Yes.
black holes as well.
Yes. We have there was a famous guy in relation to black holes called John Wheeler, and he wasn't originally from Youngstown, but he lived in Youngstown for a huge chunk of his childhood because his father worked at the Mahoning Valley Public Library just across the street from YSU.
Was the head librarian there?
Oh,
He
he's
was
the
in
head librarian.
charge of the Mahoning
Nice.
Valley Public Library. Yes.
Do you want to talk a little bit about him, Kurt? I think you know
Well, why
more
don't
about
you
him than I do.
start where we get black holes from with that guy
Yeah.
with the mustache, and then I'll go into him.
We should probably take a couple steps back just to give some context in case many of us probably know at least a little bit about black holes, but
And not
honestly,
from the Disney movie either.
even experts who study black holes and who spend their whole career studying black holes can only tell you three things about a black hole. They can tell you of a discovered black hole. They can tell you its location, its mass, and what direction it's spinning. Three things. That's all that experts could tell you about a black hole while they're studying it. That's the most information you're really going to get. But black holes were theorized way back in 1915. Well, I say way back, that's not even really that long ago, about 100 years ago.
As far as science goes, that's not a long time ago at all.
Yeah, it's not. By a fellow named Albert Einstein, when he was writing his theory of general relativity, and it was when he was describing the sort of the fabric of space-time as we understand it, he theorized that black holes could exist, this area of sort of like a collapsed space-time where the gravity is just incredibly immense, so immense that nothing could escape its pull, not even light.
Yeah, along those lines, his theory was so radical that there was no way to prove it when he did that. The first proof actually came in the 1920s. There was an eclipse that happened, a total solar eclipse. It happened over South America and Africa, and some scientists from Great Britain went to these two locations, and the way they proved Einstein's theory worked was when the moon blocked the sunlight, they knew where the stars behind the sun should be, but the sun's gravity made them appear to be in a slightly different position, and it directly proved Einstein's theory of relativity.
Yeah, and that was lensing, which is sort of what's happening in my background here. The black hole is distorting space around it. As Kurt mentioned, this is something that was theorized and talked about, sort of like we theorize and talk about wormholes and white holes. These are
Dark
something.
matter and all sorts of stuff.
Yeah, there's a lot of things even today that we understand and can describe with math, but we have not found in the natural world. And so that was the case for black holes for decades until 1964, when a black hole was discovered in the constellation Cygnus, that we saw it was a blue supergiant star that something was sucking sucking that star out, like it was sucking the outer layers of that star and draining it. And that was the first confirmed black hole.
By the way, Paul Starkey says Youngstown is a black hole, just so you know. First comment to pop up there.
So let's see. So that was discovered in 1964, but Wheeler was before then. He was in the 20s, 30s time frame when black holes were still kind of a theory, but people were talking about them.
Right. He was born in 1911. He actually lived to be 96. He lived till 2008, actually. Wow. But he spent his childhood years in Youngstown, but then he got his degree from Johns Hopkins. He was actually involved with the Manhattan Project during World War II, the formation of the atomic bomb, because of his work with quantum physics. But he went on from there to do some other work too. He was working on mathematical extensions of Einstein's general relativity in 1957, and he introduced the concept and word wormhole to describe hypothetical tunnels in space-time. Basically, what happens is when a big star dies, it collapses and all this stuff gets pulled into the center, and the gravity is so strong it actually punches a hole into space-time. It basically makes a pit that is so deep not even light can get out of the pit, and if the hole is so deep it could actually tunnel to another part of space-time. That's what a wormhole is. Wheeler and Niels Bohr did more research on it and determined that wormholes are not stable. So you can't actually go to a black hole and use a wormhole to pass through time and space to another location. They're too unstable for that. We'll get into the ways a black hole can kill you a little bit later, by the way. There are a lot.
We should do that. We should do that for sure. Paul asked, do you believe there are portals to other dimensions? So that kind of touches on what you were just talking about, that black holes. I mean, it's theorized that on the other side of a black hole would be something called a white hole, which would put you in a different part of space-time. So you would be in a different part of space. And I'm not 100% sure on this, but I think a different time as well. Maybe not. I have to look that up, I guess. But
yes, another thing that I've seen a lot of speculation in science fiction, but cannot actually be proved because we cannot go there, because the gravity is so strong near a black hole. It distorts space-time, and not only displaces stars in the sky, but time for a person near a black hole slows down. So you can actually travel through time into the future. You will not appear to age while everything speeds up around you. And then when you come out the other side, you're into the future.
Yeah, that's so cool. So if you, this is like a thought experiment, because I don't think you really could actually do this.
No,
but if you could get close to a black hole, you would, time would slow. So say Kurt is watching me go into a black hole. He's the observer. Kurt would see me slow way down, and I would look like I was frozen in time. But what's actually happening is that I'm experiencing time much slower than he is. And if hypothetically I could, after a year in my time frame, like for me on my spaceship or whatever, it takes me a year or some time like that to somehow figure out how to escape the gravitational pull of that black hole, which that would be tough. But hypothetically, if I would have only aged a year, and Kurt would have probably been watching me for like millions of years. So effectively, I would have traveled through time. So gravity absolutely, at this level, especially when we're talking about black holes, distorts time.
Yeah, and I remember when I was taking quantum mechanics, there was a lot of my professor would say something, and I'm like, if you say so. So,
Yeah.
there's a lot of that.
I love it.
One really cool thing with the term black hole itself, too, with John Wheeler, he did not coin the term, John Wheeler, but
The black hole.
the term black hole. He used the term black hole in 1967 during a talk at the NASA Goddard Space Institute, and the term had been used early in the decade, but the reason he used it was Wheeler said this term was suggested to him during the lecture when a member of the audience got tired of hearing him say gravitationally completely collapsed object. So
I love
it's
that.
much easier to say black hole instead of gravitationally completely collapsed object. So
Gravitationally completely. That is what a black hole is. Gravitationally completely collapsed object, but black hole is so much cooler.
Yes. So he was a very big pioneer in the field of quantum gravity, and he and another gentleman, Bryce DeWitt, created an equation that then Stephen Hawking described as the equation governing the wave function of the universe. So his work was instrumental leading up to the work that Stephen Hawking did.
Yeah, and so in 1964 is when we first discovered the black hole. Before then, these guys you're describing, they were all theorizing, much like we theorize about dark matter and dark energy today. But after a black hole was discovered, the search was on. And so recently in the news, Dr. Andrea Ghez, an astrophysicist, recently won a Nobel Prize in physics. She was only the fourth woman ever, and it's like 101-year history to win a Nobel Prize in physics. But she and the team discovered a supermassive black hole in the middle of our Milky Way galaxy, which I think it's such a cool story. But to preface that, supermassive black hole, remember we only can say three things about a black hole, and one of them is mass. So supermassive black hole is defined as a black hole that's somewhere in the millions to billions of times more massive than our sun. We call it solar masses. It's like an easy way to measure something that's really massive in the universe. So millions to billions of solar masses. That's the black hole's mass we're talking about.
Something to keep in mind with these big ones that are at the center of galaxies. We think that most large galaxies have black holes at the center, but the reason they're so big is because galaxies just aren't out there in space by themselves.
No.
They're constantly interacting with other galaxies, and I can't remember the exact number. I think they speculate our galaxy has swallowed like 3 other galaxies at some point.
Yeah.
So
I think we speculate that because of the Magellanic Clouds, right?
The Magellanic Clouds, they split those off. They see the debris of a couple other small ones, but we may have interacted with other more massive ones and eaten their black holes into our black hole at the center of the Milky Way, which is one of the things that gets it big. It keeps pulling in the black hole from other galaxies.
And so in a very elementary sort of way, you could think of black holes as, they're heavy. There's a lot of gravity, right? So they're sort of like go towards the center, and they would attract one another. But that certainly is the case when they reach a certain distance. And our understanding of gravity can very accurately calculate that distance if you know the mass of that black hole. But there's actually millions of 10 million to a billion black holes theorized in our galaxy.
It's only super huge stars that can collapse to become black holes. And astronomers have theorized that looking at the number of these supermassive stars that we see in our galaxy, in our Milky Way, there must be somewhere between 10 million and 1 billion of these things in our Milky Way. Keep in mind, our Milky Way is somewhere between 100 and 300 billion stars. So it's only a small fraction of the stars in the Milky Way, but they're not all falling into the center. These are out around, and we can only see them, when we get this gravitational lensing of stars or other objects behind them, and it passes close by to them. We speculate they're there, but we have no way of imaging them.
Yeah, it's actually kind of difficult to discover these smaller black holes that you're talking about. And by the way, if you're like, why does the stars create black holes? What is that all about? You'll learn all about that on our Saturday show. This Saturday, keep looking up. We're going to be talking about a star's life cycle and how that can happen. So if you're curious, come see us.
Saturday at 8.
Saturday at 8. That's right.
Right here, right where you're watching now. Here at 8. Saturday.
But the black holes are very, very difficult to detect, especially those smaller ones that are not what we would call a supermassive black hole, because even the supermassive black holes are detected using indirect methods, or have been until very recently. So Andrea Ghez, for example, her and her team discovered what we call Sagittarius A star, because that's the black hole in the middle of our galaxy. And it's called that because if you're on Earth looking up in the sky, it's in the constellation Sagittarius. That's bam, right to the center of our galaxy is Sagittarius. So they've discovered that not because they took a picture of a black hole, but because they saw these stars that were orbiting something that's black, right? Not even light can escape a black hole. So these stars
not
were
even
orbiting.
that, because there was just so much stuff down there. They looked at the orbits of these things.
Yes.
And they would get close and they'd speed up when they got near something, then they'd slow down as they moved away. And they figured out that point that everything was orbiting around down at the center.
And again, thanks to Einstein, we are like we can very accurately understand and describe what's happening there due to gravity. Even if we can't see the black holes there, we can observe the orbits of those nearby stars that are having that are being pulled and affected by that black hole's gravity. And we can calculate, Andrea Ghez and her team was able to calculate things like it's the mass of that black hole.
And they couldn't do it in the light we see with our eyes either. They had to do this across the entire electromagnetic spectrum, because there's so much stuff between us and the center. Even the Hubble Space Telescope couldn't look through everything. So we had to look in X-rays and radio waves. And radio waves are actually very useful for this because they can penetrate a lot of stuff and get down in there. But actually, it was Andrea Gez's team with the Hubble Space Telescope. One of the first things it did was prove there was a black hole at the center of our galaxy, which was a huge revelation when it first went up in the early 90s.
Yeah, so and this is that was around when this was discovered in the 90s. Maybe it was mid to late 90s.
They had data. Hubble went up in 90. I think it was as near as like 92, 93, 94. One of the very first things they imaged after they corrected for the spherical aberration was finding the black hole at the center of the galaxy.
So we have another question from Paul. What is the furthest black hole ever observed?
Well, as I said, we speculate that nearly every galaxy has a black hole in the center. And we now have seen galaxies as far away as 13 billion light years away from the Earth. However, we haven't seen the black holes in there. There's only one other one. There's only one that we've actually seen, and it's over my shoulder right here.
Yeah.
And Tiffany can talk a little more about that because she was involved with a small part of the team that's.
I just visited. I was a tourist, so.
Yeah, but you were actually at the observatory.
Yeah. So the image over Kurt's shoulder is from M87. It's a supermassive black hole in a enormous galaxy that's in the Virgo constellation.
I talked about how galaxies merge It's now looks like a giant egg because so many galaxies have merged. Spiral galaxies eventually turn into eggs or elliptical galaxies when they merge. And this is a massive one that's eaten lots of galaxies.
So M87, I did Google this, guy, sorry, but because I always forget, it's incredibly far away. Okay, it's 53.5 million light years from Earth. Okay, so incredibly far away, but it's so massive that it was actually a great candidate to try to take a picture of its supermassive black hole.
Thanks to the Hubble Space Telescope, before we took a picture of the black hole, we saw this enormous jet of material,
yes,
even bigger than the galaxy, shooting out both sides of it.
Yes, and so we were able to kind of survey, and also it also helps like orientations when you're looking out into space at different galaxies. Are they face on? Are they face on where we can see the galaxy? Are they edge on? A lot of galaxies are going to be somewhere in between. So you have to consider that. You have to consider their size and their distance and different things like that. But considering making these sort of practical considerations, the M87 was considered a really viable candidate for trying to take an actual photograph of the black hole in its center, its supermassive black hole. But the observing power that you would need for a picture like this would basically be, you can imagine because this is mostly radio waves, so it would be like a satellite dish. That's what radio telescopes look like. They look like big radio dishes. So you could imagine, to get an image of a black hole that far away, you would need a satellite dish about the size of planet Earth. Yes, our entire planet. And no, we can't physically build one that big, but we have recently had advances in technology that allows us to sort of network many radio telescopes together. And if they are all taking data at the same time, pointing at the same place, then they can, it's a process called interferometry, if you're ever interested in looking it up, but it's really fascinating. And they can basically take pieces of data from all these different observatories and put them together. And so that's exactly what happened. There was a project called the Event Horizon Telescope that is responsible for that picture that you see on Kurt's background. Telescopes in the Antarctic, telescopes in Chile, telescopes in Hawaii, New Mexico, I think Canary Islands, Australia, all over the world, literally across this planet. We had the world's best radio telescopes, billions and billions of dollars invested from all kinds of countries. They all got together and decided that this pursuit of taking this photo was important enough. We're all going to work together. They all pointed their radio telescopes at the same time in the same place. And this took a long time, a month to get these several attempts down. And anyway, and then there was a lot of different algorithms they had to figure out, and just the computing side of things. So it was just this monumental task that took thousands and thousands of people just to get that image that you're looking at above Kurt's shoulder.
Yeah. What you're actually looking at, I can't do it without making my background go away. But the bright stuff you're seeing is stuff that's still outside the black hole. It's material that's falling into the black hole. The black hole's not sucking it, it's pulling it in, but that's still stuff outside. And then that dark center spot is what we call the event horizon. It's also known as the Chandrasekhar limit. And inside of that, not even light can escape. Yeah. So we can't.
Sort of the point of no return for light.
Exactly. So the actual black hole is a lot smaller than that black spot in the middle, but that's as far down as we can see. You notice that down here, you see all these lines. This is actually resolution over the last few months since they've had this image. Mm-hmm. They've actually refined it, and these are due to the magnetic field of the black hole. They were able to put these in.
Yeah, the first image is a little more fuzzy than that, but you can see, so there was a lot of memes online about how it looks like a donut, but that's exactly what we theorized, which was so cool. Like, for a science communicator like me, I'm like, oh my God, it's exactly what we thought. That's so cool. And all the scientists were like, oh, it's what we thought it was going to be. They're like a little disappointed, like it wasn't something new that they had to figure out, what, like a new puzzle, you know. But we theorized that this the bottom was brighter and the top was dimmer. That is showing motion. Of course, it's a lot easier to see with this newer picture. You can see that a black hole is turning, right? It has a spin, and you can see that spin with the material being brighter at the bottom and darker towards the top.
Larry Plant has a question for us. What is the average distance between our galactic central stars, and are they in danger of being swallowed by the black hole there? And I'll answer that a little bit. The black hole has cleared a large empty spot in the middle of our galaxy. The stars get, when you're going in toward the center, they get thicker and thicker and thicker and thicker as you're going into the bulge of our galaxy. But then right down near the black hole, the gravity and the appetite has literally cleared out the stars right around it. There are only a few dozen stars that Andrea Ghez and her team were able to image, and some of those, yes, are in danger of getting sucked into the black hole. Us out here and most of the rest of the stars of the bulge are not. It's pretty much cleared out what it's going to clear out in the center of our galaxy. But the stars they imaged, there's maybe about a dozen that are still in danger of falling into the black hole.
Yeah, that's a great question.
Yes.
See, James says, would the very young galaxies we see many billions of light years away have a smaller central black hole or fewer black holes? So that's
younger galaxies would most definitely have fewer black holes, because not as many giant stars will have died. This is the area of speculation. We don't know at what process in a galactic formation the black holes form. We've only just recently been able to see 13.5 billion years and see these very young galaxies, and they just look like little on a Hubble plate. So people are still trying to figure out exactly when they become spirals and what process it takes to get the black hole in the middle. That's still very, very young. We call that cosmology, and it has nothing to do with putting on makeup. So.
I love your description of early galaxy. What?
That's
good.
That's what it looks like to me. Oh, it's a peanut. Oh, it's Mickey Mouse's ear. You know, they don't look like much, but it is cool that the Hubble Space Telescope can take a picture of the sky and see that far back. Now, some of you may know Hubble is getting to the end of its life. We no longer can service it because the space shuttles are not running anymore. One of the very last space shuttle missions was one last upgrade on Hubble. We're having some troubles with the gyros with Hubble, but the next generation of space telescope is called the James Webb Space Telescope, and it's getting really close. Then again, we've been saying that for the past several years.
I will not hold my breath.
Yes, exactly.
Sorry to all my friends on that project, but
now I don't want to get too much into explaining what this is, but when you get far away, because the galaxy is expanding, we get into something called redshift, which means that when stuff moves away from you, what we see in the spectrum moves down into the infrared and so forth. The James Webb Telescope isn't going to be looking so much in the visual range like Hubble did. It's going to be looking more in the infrared, so it can see even further away than Hubble can. And so some of these questions you may be asking about the things may be answered when the James Webb Telescope gets launched.
We have another question. So Paul asks, from his 18-wheeler, nice.
Yes, I saw that.
Can a larger black hole swallow a smaller one? And
that is how we think the central black holes in galaxies
have formed. Yeah, but they have to be close enough, right, to get gravitationally bound or be gravitationally attracted to one another.
Well, once again, this is theory.
And the mass actually matters.
Yes, we assume that if something like that happened, there would be a humongous amount of energy released when something like that happened. We have never observed that, but it is theorized that's how this formed. Now, it's possible we see things out there called quasars Maybe that's what a quasar is two black holes forming together. We are also looking for something now in Louisiana. A site called LIGO is looking for something called gravitational waves. Gravitational waves may form when galaxies collide with one another. We've only just in the last 10 years been able to
We've confirmed that, right? That LIGO has confirmed that
it has confirmed gravitational
with two
waves.
black holes.
Was that two black holes?
Or was it two quasars?
I think it was two quasars.
But yeah, so
I'll
it's
have to look
theorized that
that
it can
up.
happen with two black holes as well. So they collide and the it's like this gravitational waves are, you can think if you think of space-time as a fabric, which is oversimplification, but it works. So let's do that. It would be like a ruffle. It would be like a wave that you would send through the fabric. So literally time and space is compressing and contracting. Compressing and contracting like a wave.
We're part of the fabric. It's very, very hard to figure out the fabric you're
on.
So
your literal, the atoms in your body, the atoms in the desk you're sitting in, the 18-wheeler you're sitting in, would be compressing and contracting, but your perception, you wouldn't perceive it. And which is why it's so difficult to discover gravitational waves. We could do a whole thing on gravitational waves. We should get into that. But they're super cool.
I used to say to Professor Shearer, if you say so.
Yeah, exactly. And we didn't even talk about my favorite tidbit of knowledge about about black holes, which is what happens if you fall into one.
Yes. And let's just say nothing good.
Yeah, preface it. Let's just start there.
Yeah. There's all this speculation about being able to use black holes to time travel when you get close enough and you whip out the other side. We kind of do this with spacecraft here in the solar system, right? This is how we got New Horizons to be the fastest spacecraft and thing. We pass it close to a planet, use the gravity from the planet, whip it around, and it picked up speed as it goes by. Now, when you're talking about doing that with a black hole, you're talking orders of magnitude more, but there are some serious problems when you get that close to a black hole, Tiffany.
It's called spaghettification.
That's just one. First, you got to worry about the radiation.
Yeah,
that's get that close.
Yeah.
As I said with M87, this guy here, it has a jet of super high energy gamma waves shooting out.
Which would fry you
hundreds and thousands of light years out of the center of the milk of M87.
Yeah, think about UV rays and how they burn your skin, and gamma rays are like way higher energy.
Yeah.
They'll fry you in seconds or less. Very quickly.
Yeah. It looks like Wile E. Coyote when he drops a match on his head.
But if you made it that far, when you reach the sort of the event horizon there, or a little bit before then, you will stretch out in one dimension, like a spaghetti noodle, which is why they call it spaghettification.
That's because the gravity is so intense. You have higher gravity at one end and less gravity at the other, and it actually pulls you.
Exactly. So if you're going in feet first to that black hole, the gravity that your toes are experiencing versus the gravitational force at the top of your head are so vastly different that you're just stretched out like a noodle, but to an extreme, like, so you're stretched out so far that even the atoms that make up your body break down. Even they are stretched out like noodles. So at the subatomic level, just totally destroyed. So
and then all those subatomic particles go past the event horizon and get mashed together in an area so dense there is no space in between them. And that's why a teaspoon of material from a black hole would weigh as much as our sun, for example.
Yes, incredibly dense. Yeah, black holes are cool but deadly. So it's my job. One of the things that I love about my job is that I get to describe this to 7-8-year-olds regularly. They want to know how you could die, how you would die by a black hole, or want to know what happens if you get in your black hole.
Paul Starkey has a great analogy. You're probably too young to remember this. Stretch Armstrong. If anybody remembers the old Stretch Armstrong, that's exactly what it would be.
So I am a lot nicer to defend myself. I am a lot nicer about that with children, but I always do end it by saying very explicitly that there are no black holes anywhere near Earth or our solar system that is going to affect us in any way. Black holes don't really move around. They're not like, rogue attackers that move around and suck things up. They just kind of hang out, and like whatever gets near them, they'll eat it up. So just don't, if you're hanging out in the middle of the Milky Way, maybe don't.
Yeah, kind of like that black bear in Austin town. If you just stay away from it, you're fine. If you see it, that's okay. Just don't get too close.
Larry asked a great question. What happens when neutrinos pass through a black hole?
Well, those jets that are coming out of N87 actually have not fallen into the black hole. It's just energized them so much it's shooting them out. I don't know if we know. Do you?
No, I know that neutrinos are like a elementary particle. So a subatomic. So
still affected by gravity, though.
Yeah. And we do know that that stuff does escape black holes. We call it Hawking radiation after the guy who discovered it. And I don't know
the work of John Wheeler.
Yeah. So that's a great question. Neutrinos have basically no mass.
Yeah, well,
I don't know.
Yes, you're getting into the realm where you go past us and you go to the people who have the PhDs in our department.
But I'm curious if anyone knows. We might not know as a human species. We might not know that answer yet.
Yeah, the one person I would pose that to, but we'd have a very, very long segment, would be the one professor we have at YSU, Dr. Mike Crescimano.
Oh gosh!
If anybody I would ask, he would be the one I would ask.
We have so many hallway conversations, y'all.
He gets so enthusiastic about things that would go a long time.
Because he's not an astronomer; he's a physicist, but he loves thought experiments. And I'll like go in the before times. I would go and get a refill in my bottle of water, and Dr. C would be out there, and he's posing like this interesting, like, hey Tiffany, what do you think about such and such? And then we'd end up talking for 30 minutes about this theoretical thing, like what would happen to a neutrino inside of a black hole. So yes, perfect person to ask, for sure.
So you see any other questions for us there?
I don't see anything, but thank you guys for asking some really wonderful questions. If you have questions after the show, I know a lot of our folks watch our programs after the fact, which is totally fine. We'll be keeping track of the comments and we'll respond to some of your comments after the fact if you oblige and leave them for us.
Other than that, remember, we are going to be talking about Life and Death of Stars on Saturday. So some of these things might come up again. So maybe we'll have some answers then too. So tune in Saturday at 8 p.m. right here. Same bat time, same bat channel.
It's 8 o'clock.
Different bat time. The same bat channel.
Well, thank you guys so much for joining us tonight. I hope to see you this Saturday or Keep Looking Up. But until then,
one other thing I want to forget, Tiffany, another preview. We were talking about this picture behind me. Just last week, we have upgraded the gallery in the Ward Beecher Planetarium. And when we come back live this fall, one picture we got is what M87 looks like. And then it zooms in and shows you the jet, and then it zooms in and shows you this. So we actually have a picture to give you an idea
of the galaxy, and then of this black hole image. It's just really cool. Gives you a little bit of a sense of scale too. Pretty cool.
So when we're right now working on a plan to be reopened this fall. So when you do come back to the Ward Beecher Planetarium, you'll want to be sure to check that out.
All right. Well, we try to keep these down to like 20-30 minutes, and that didn't happen tonight, but that's just
because black holes are
that cool.
No.
Well, that too, but black holes are also really cool.
Yeah.
So thank you for joining us tonight, and keep looking up.